Hello everyone and welcome back to the channel CSAITTTL. Today we're diving into the big table problem. We've all been there. Storage limits hit, query slows to crawl, and write contention turns your database into a bottleneck. The monolith is falling and the pressure is on. But remember, where you decide to break that monolith apart is the difference between a system that scales and one that shatters. Before we get into the architecture, please like, share, subscribe, and share this video. And for those looking for the full roadmap, head over to www.bitbytoken.com. We have deep dives on everything from software and data engineering to AI and machine learning. It's the ultimate resource for your career growth. Here, that's what, let me provide a bit of a walkthrough through this. These are different components, software, data engineering, machine, AI engineering. For each of these, you can look into the fundamentals and then the sample solutions. And the solutions have been as detailed as possible. We have functional requirement, we start with non-functional requirements, then we move on to detailed design. We consider the data model and also we considered several sequence diagrams and all those details. Do check this out. Let us know about how your experience with this site is. Okay, let's get started with our topic today. Before we go distributed, we have to respect the machine. You're physically bound by the CPU, RAM, and disk I/O of your server. No matter how clever your indexing is, you are eventually going to hit this monolithic ceiling. The goal is to exhaust the vertical potential of your hardware before you introduce the complexity of the distributed system. Don't reach for a cluster until you have squeezed every drop of performance out of the box you already have. So you have optimized, but you still need more room. Meet partitioning. Think of this as the reorganizing a studio apartment. Everything is still in one building, managed by the same database engine. The application fire a standard select, and the database engine handles the magic of partition pruning to route to the correct internal segment. The beauty here, the application doesn't even know what happened. It's entirely transparent. The heart of any partitioning strategy is the partition key. A good key has high cardinality and aligns with your most frequent query patterns. If you pick the wrong key, you get partition skew, where one segment is overloaded while others sit idle. Whether you choose range for continuous value, hash for uniform distribution, or list for categorical separation, pick your key wisely. It is a difference between a performance system and a massive headache. Now, what happens when one machine just isn't enough? We embrace the philosophy of systems like Cassandra and DynamoDB. We abandon the impossible supercomputer and instead build a fleet of inexpensive commodity nodes. This is the transition from a single database instance to a cluster, a collective logical system where each node carries its own CPU, RAM, and disk. This is where we enter sharding. Unlike simple partitioning, sharding happens across the network. Each shard lives in a separate server, and no single machine holds the whole truth. Because the database engine no longer sees the full picture, you have to introduce a routing layer, middleware that sits between your app and the shards to ensure your request lands at the right address. You're now officially in distributed system territory. Let's talk about the shard key, the master decision. It must be immutable, but there's a trap. If you shard a social media feed by a created ad, all your news traffic will dogpile into a single active shard. This is the hot shard meltdown. Your system is distributed, but your throughput is effectively limited to the capacity of that one single overwhelming node. When nodes come and go, you don't want to shuffle all your data. That's where consistent shaving saves the day. By mapping keys and nodes into a 360-degree ring, you ensure that adding a node only impacts its immediate neighbors, not the entire cluster. It minimizes the resharding tax and keeps your cluster stable even as you grow. For more details on consistent hashing, check out my series on consistent hashing. There are much more details available there. Okay, moving on. Systems fail. That's just a fact. If a node dies, you can't have 33% of your users lose access. We need backup librarians, or as we call them, replicas. With a replication factor of 3, if your primary node goes down, a replica can be promoted instantly. Service is restored with minimal downtime. It's not just about scaling, it's about surviving the inevitable. When you replicate, you face the consistency trade-off. Synchronous replication keeps everything perfectly in sync, but it hurts your write performance. Asynchronous application lets the primary race ahead, but you introduce a stale window where readers might see outdated data. You have to tune this per query. Maximizing write throughput almost always costs you temporary inconsistency. Don't forget the other axis, vertical partitioning. Sometimes the problem isn't about the number of rows, but how wide they are. By stripping away cold columns like massive user bios or historical logs and keep odd columns in their own table, you drastically increase your cache hit rate. A simple select that fits more rows into each disk page is a massive win for performance. Why do we call sharding a last resort? Because of the trade-off tax. You're trading operational simplicity for distributed complexity. You get hit with a scatter-gather latency for cross-shard queries, and your asset guarantees are shattered. Now you're dealing with distributed transaction. You break the database abstraction you once took for granted. Only go there when you have no other choice. Here is the 500 million user architecture in practice. In, it's everything working in concert. Consistent hashing on the router plane for horizontal scale, replicas for availability, and internal partition by ear for query speed. It's a multi-layered approach. It scales write out, read out, and queries deep. This is how the giants do it. The industry's rule of thumb is simple. Exhaust vertical scaling first, then look to caching and indexing. Only then consider internal partitioning and leave sharding as your absolute last line of defense. Instagram and WhatsApp stayed on as massive monoliths for years by mastering this exact progression. Stay at the simplest layer that satisfies your requirements as long as possible. To wrap up your interview debrief, remember the sharding is just a specialized form of partitioning. Physical distribution is the differentiator. The engineer who gets the offer isn't the one who memorizes these terms. It's the one who articulates why they chose a specific shard key and can anticipate its failure modes. So, what's the biggest challenge you have faced when scaling a database? Share your war stories in the comments. If you found this session valuable, please like, share, and subscribe. And I'll see you in the next one.